Well, I squeezed my work for the second part of the question, the velocity, instantaneous velocity at 3 seconds, in at the bottom of the page there, and realized afterwards, oh, look at that, I gave myself some extra space. So we had already calculated on the last podcast that it was 2 meters per second was our instantaneous velocity, our instantaneous rate of change. If we want to find the moments of time at which the velocity is 0, come on. Well, it'll come underlined at some point. That means that, come on, it's always really slow in the beginning. All right, there we go. So if we're looking for when the velocity is 0, it means our instantaneous rate of change is 0, right? That's when our velocity, when that velocity at a moment's time is now 0. So to find that, we're going to set our equation for the instantaneous rate of change. Okay. And so we have, in a really easy problem, 2t minus 4 equals 0. Add 4 to both sides. 2t equals 4. Divide by 2. So at t equals 2 seconds, the velocity equals 0. And we'll spend a lot more time on problems like this. Matter of fact, I have a whole lesson of problems like this, looking at when velocity is 0 and other assorted interesting problems. But here's one example. Right? So when we're looking for something like this to know when exactly our velocity is a certain value, it's when you need to find when your instantaneous rate of change is that value. So you'd have to find what equation represents your instantaneous rate of change. So in this case, our equation was 2t minus 4, and we just needed to set that equal to 0 to find out when our velocity would be 0. Right, so geometry and algebra. We use a little of both in this particular lesson. So a secant line models the average rate of change over an interval, average velocity, average rate of change. It's the same thing, except we can have changes of things other than velocity, but average velocity is an example of average rate of change. So if we compute the change in y over the change in x, we get the average rate of change, or the change in the value of the function over the change in x or time, or whatever our independent variable is. The tangent line models the instantaneous rate of change at a velocity. Right? So it's the instantaneous rate of change at a point. So it's our instantaneous velocity or any instantaneous change. It doesn't have to just be velocity. So therefore, if we compute the limit of the change in y over the change in x as that difference between our points goes to 0, in other words, f of x naught plus h minus f of x naught, and x naught just some point, divided by h. As h goes to 0, we find that limit, then we'll find our instantaneous rate of change for y equals f of x when x equals x naught. So sometimes we'll get a constant, but many times we get a function, and we use that function for our instantaneous rate of change, and we evaluate that to find instantaneous rate of change at some moment in time. And let's look at this problem. So a spherical balloon is inflated. Find the instantaneous rate of change in volume of the balloon with respect to its radius when the radius is 10 meters. Well, the first thing that would help is for you to know what the equation for volume is. If you don't know that, then you're kind of at a loss on this problem. So the equation for the volume of a sphere, and by the way, in calculus we have interesting spherical balloons. Not those balloons you're used to seeing, but spherical balloons. They're easier to compute with. All right, so it's a lot easier to work with a spherical balloon than it is some oblong, funny-looking egg-shaped balloon. All right, so volume is 4/3 pi r cubed. All right, so laid out the volume of a sphere. All right, so we're told when So when radius is equal to 10, that means we're going to substitute this value into the instantaneous rate of change, which is a function. All right, so let's take the limit as h goes to 0. If you notice here, it says change in r. So your change in your radius is where h is going to represent the change in the radius. Right? I always pretty much work with h as h goes to 0. And what is h? H is just the change in your independent variable. In this case, it's r, right? Because I have an r in my equation. If I had a t, it'd be t. Right? So as the difference between the two values in time go to 0. So the difference between radius at point 1 and point 2, as that difference goes to 0, we're taking that limit. That's what h is. So it's the limit as h goes to 0, and that's just the change in the radius. That difference is going to 0 here. So I'm going to plug in r plus h. Right, so we have 4/3 r plus h minus 4/3 r, all divided by h. Now, if you'd like to make this a little easier on yourself, if you notice here, 4/3 is technically a scalar. Notice that both of those are being multiplied by 4/3, right? It's part of the equation. So the limit of a scalar times a function is the same value as the scalar times the limit of the function. In other words, I can take that scalar out right from the beginning and just multiply by 4/3 at the end. Right? So the limit as h goes to 0. Oops, I almost forgot my cube there. Okay. And now at least that's one thing we don't have to deal with. Right? We don't have to distribute that 4/3 all the way through and then combine our terms. Right? So we'll just distribute the 4/3 at one time. Right? So now we have r plus h cubed minus r cubed. Right? All divided by h. So I'm going to have to use this area. I'm going to run out of space. Equals 4/3 times the limit as h goes to 0. Right? So now is when Pascal's triangle would come in handy to know that, huh? For multiplying, cubing r plus h. Of course, you could also just, multiply r plus h times r plus h, and then multiply the results by r plus h. But if you remember the sequence of Pascal's triangle, you'll remember how the coefficients go. And if you remember binomial theorem, that'll help you with how the exponents go. So when I cube r plus h, I'm going to have r cubed. And actually, I'm going to write it like this, just to help you remember how to cube this. So r cubed times h to the 0. Well, anything to the 0 is 1. So there's not going to be an h. There's not going to be an h at all. It's just going to be an r cubed. I have a plus, which makes things nice because these are going to both be positive. Plus 3 times r squared times h to the first. Notice that the exponent on r is going down and the exponent on h is going up. Plus 3r h squared plus r to the 0 and h cubed. So if you remember Pascal's triangle, the third row will go 1, 1, 3, 3. Those are the coefficients. So just helping you out with the multiplying. All divided by h. Oops, we forgot somebody. I forgot about the minus r cubed. Hold on. It's because I ran out of space. We spent so much time cubing. Come on, everybody move over just a little bit. Minus r cubed. Now you don't have to write an h to the 0. That was just in case you didn't remember how the coefficients went and how the exponents went. So I'm going to simplify that. 4/3, the limit is h goes to 0. That's r cubed plus 3r squared h plus 3RH squared plus H cubed minus R cubed all over H. And the R cubed is going to cancel, right? Because those are opposites. So we have 4/3 times the limit as H goes to 0. And now I just have 3R squared H plus 3RH squared plus H cubed all divided by H. Well, if you notice, everybody has an H. This would be an indeterminate limit if I plugged in. Let's just pull the H out. So we have 3R squared plus 3RH plus H squared divided by H. That will cancel, right? So, and I'm going to plug, oops, I forgot to write the limit. Limit as H goes to 0. So now let's plug in the 0. So we have, I'm still not going to distribute this 4/3 yet. So we have 4/3 times 3R squared plus 3R times 0 plus 0 squared. Well, notice that the only thing going to be left is the 3R squared. So we have 4/3 times 3R squared. Those 3's will cancel, so that's 4R squared. This function here gives us our instantaneous rate of change. Did I give myself space on the next page? Because it's getting kind of crowded over here. Nope. Let's give ourselves a little bit of space, all right? It was 4R squared. All right, so our instantaneous rate of change here is found using the equation 4R squared. We wanted to know what it would be when our radius is 10. Right, so our instantaneous rate of change is going to be 4 times 10 squared, or 4 times 100, or 400, and if you were like me, you didn't remember what the units were. Meters per, there's no change in time. Second, I say meters per second. So 400 meters per second, this is our instantaneous rate of change in the volume. That's how fast our volume is changing at the moment that the radius is 10 meters. Okay? So this instantaneous rate of change in volume is for at the moment the radius is 10 meters. Not 10.1, not 9.999, but 10 meters. At exactly that instant in time, our rate of change is 400 meters per second. Okay? So you're actually learning something very powerful. You may not realize it right now, but you don't have to find just change over time. You can find change at a moment. So a line that is tangent to a curve has two properties. The line shares a point with the curve in question. At that shared point, the derivative of the curve is equal to the slope of the line. Make sure this is in your notes. Hunt around. This is another key idea. So we had the key idea that as that difference goes to 0 between our points, we have the slope of the line, the slope of the actual function itself. We've now learned how do we calculate out that instantaneous rate of change by taking a limit, as the difference between those 2 points goes to 0. And now we have the sentence here, derivative of the curve is equal to the slope of the line. I'm just going to write key idea right now, and then I'm going to explain it a little later. So here's the summary of, I'm going to stop actually at this point, right here at this point, and pick up on Tuesday, and we're going to look at equations of tangent lines for curves. Right? And this is just a very brief introduction to it. we have many more things to come back to, particularly that number 2 there, the derivative of the curves equal to the slope of the line. We're going to talk a lot more about that in this lesson and an upcoming lesson. All right, that's all for this lesson. Well, not all for this lesson, but it's all for this podcast. Bye.